Welcome to English Simplified Channel. Today, we're diving into pre-experimental data analysis and hypothesis testing. Whether you're new to data analysis or just brushing up, I'll walk you through each step. We'll manually calculate basic statistics and perform a hypothesis test together. Let's get started. In this video, we'll start by understanding what pre-experimental data analysis is. Then, we'll calculate the mean, variance, and standard deviation using simple formulas. Finally, we'll perform a paired t-test to see if the changes in our data are significant. Let's get started. Section 1. What is pre-experimental data analysis? Before diving into data analysis, it's crucial to ensure the data is accurate and complete. This is known as pre-experimental data analysis. Think of it as a way to double-check your data, making sure there are no errors or missing information. For instance, if you're analyzing test scores, you'll want to confirm that all scores are recorded correctly and that each student's score is included. This step is essential to lay a solid foundation for further analysis. Section 2. Example scenario and data collection. Let's say you're a teacher testing a new teaching method. You've collected test scores from 5 students before and after applying this new method. Here's the data we'll use. Student score before, score after, A, 70, 75, B, 82, 88, C, 78, 85, D, 65, 70, E, 90, 95. We'll use this data to calculate the mean, variance, and standard deviation of scores before and after the teaching method. Then, perform a paired t-test to determine if the observed changes are statistically significant. Section 3. Calculate mean, variance, and standard deviation. Let's first start by mean calculation. The mean, or average, gives us a central value for our data. To calculate it, you add up all the scores and divide by the number of scores. Formula, bar x nin. Breaking down the formula with example data. Bar x, this symbol represents the mean or average score. This Greek letter sigma represents summation, meaning add up all the following values. Xi, this represents each individual score. In our example, these are the scores before and after applying the new teaching method. Scores before 70, 82, 78, 65, 90. Scores after 75, 88, 85, 70, 95. N. This represents the total number of scores. Now, let's calculate the mean score before and after applying the teaching method. Mean score before, bar x equals 70 plus 82 plus 78 plus 65 plus 95, frac 385, 5 equals 77. Explanation. We add up all the scores before the teaching method, 70 plus 82 plus 78, 65 plus 90, which equals 385. Then we divide by the total number of scores, which is 5. So the mean score before the method is 77. Mean score after bar x equals 75 plus 88 plus 85 plus 70 plus 95, 5, equal frac 413, 5 equals 82.6. Explanation. Similarly, we add up all the scores after the teaching method, 75, 88 plus 85 plus 70 plus 95, which equals 413. Dividing by the total number of scores, 5, gives us a mean score of 82.6. Summary. The mean score before the new teaching method was 77. The mean score after the new teaching method was 82.6. This suggests that, on average, the student's scores improved after applying the new method. Let's continue to standard deviation calculation. The standard deviation is a measure of how much the individual scores in a dataset deviate on average from the mean. It gives us an idea of the spread or dispersion of the scores around the mean. Formula: S equals square sum equal 1n xi minus bar x square n minus 1. Breaking down the formula with example data, SS, this represents the standard deviation. This symbol represents summation, meaning add up all the following values. Xi bar x square, this is the squared difference between each score, xi, and the mean score, bar x. Squaring ensures that all deviations are positive and avoids canceling out positive and negative differences. n-1. This is the total number of scores minus 1, which is used to account for the degrees of freedom in the dataset. Let's calculate the standard deviation of the scores before and after applying the new teaching method. Step 1. Calculate the mean from earlier. Mean score before, 77. Mean score after, 82.6. Step 2. Calculate the square differences for scores before. Formula, xi bar x2, example calculations. For the score 70, 70 minus 77 squared 2 equals minus 7 squared 2 equals 49. For the score 82, 82 minus 77 2 equals 5 2 equals 25. For the score 78, 78 equals 1 squared 2 equals 1. For the score 65, 65 to 77 2 equals 12 squared 2 equals 144. For the score 90, 90 77 2 equals 13 3 equals 169. Step 3. Sum of square differences for scores before. Formula sum I equals 1n, xi minus bar x2, example calculation. Add up all the square differences. 49 plus 25 plus 1 plus 144 plus 169 equals 388. Step 4. Calculate the variance. Formula S2 equals frac sum equals 1n, xi bar x2, n minus 1. Example calculation. Divide the sum of square differences by n minus 1, which is 4 since there are 5 scores. S2 equals frac 388, 4. 97, this is the variance, representing the average squared deviation from the mean. Step 5. Calculate the standard deviation. Formula SC. Example calculation. Take the square root of the variance to get the standard deviation. S equals 97 approx 9.85. The standard deviation is approximately 9.85, meaning that on average, the scores before applying the new method deviate from the mean by about 9.85 points. Summary. The standard deviation for the scores before the new teaching method is approximately 9.85. This tells us that the scores tend to differ from the mean by about 9.85 points on average. Section 4. Hypothesis testing using paired t-test. A paired t-test helps us determine if the changes in scores before and after a treatment are statistically significant or simply due to chance. Step-by-step breakdown with example data. Step 1. Formulate hypotheses. We start by setting up our hypotheses. Null hypothesis, H0, there is no difference in mean scores before and after the treatment. Any observed change is due to chance. Formula, form UD equals 0. Alternative hypothesis, HA. There is a difference in mean scores before and after the treatment. The treatment had an effect. Formula has 0. Step 2. Calculate the differences between paired scores. First, we calculate the difference between each pair of scores after minus before. Formula, di equals xi after, xi before. Breaking down the formula, di represents the difference for each pair after minus before. X-axed after, the score after the treatment. Text before, the score before the treatment. Example calculation. For student A, D1 equals 75 minus 70 equals 5 minus for student B, D2 equals 88 minus 82 equals 6. For student C, D3, 85 minus 78 equals 7. For student D, D4 equals 70 plus for student E, D5 equals 95 minus 90 equals 5. Step 3. Calculate the mean of the differences. Formula sum equals 1 and square n, din, example calculation. Add up all the differences. 5 plus 6 plus 7 plus 5 plus 5 are 28. Divide by the number of pairs. Bar D equals frac 28.5 equals 5.6. The mean difference is 5.6. Step 4. Calculate the standard deviation of the differences. Formula SD equals frac sum equals 1 square n, di minus bar D 2n minus 1. Example calculation. Calculate the squared differences between each difference and the mean difference. For D1 equals 5, 5.6 squared equals 0.36. For D2 equals 6, 6 minus 5.62 equals 0.16. Minus for D3 equals 7, 7 minus 562 equals 1.96. For D4 equals 5, 5 minus 5.62 equals 0.36. For D5 equals 5, 5 minus 0.62 equals 0.36. Sum of squared differences, 0.36 plus 0.16 plus 1.96 plus 0.36 plus 6, 2.2. Variance, 2.24 equal 0.55. Standard deviation, SD equals a square root 0.55, approx 0.74. Step 5, calculate the t-statistic, formula T for D, example calculation, D equals 5.6, is D 0.74, handle 5. T equals frac 5.60, 0.74, squared 5, frac 5.6, 0.33, approx 16.97. Step 6. Compare the t-statistic to the critical t-value. Let's move on to the final step, which is comparing the t-statistic to the critical t-value from the t-distribution table. First, we need to determine the critical t-value. For our example, the critical t-value corresponds to the degrees of freedom and significance level we are using. In this case, we have degrees of freedom, n minus 1 equals 5, 9 equals 4. Significance level, alpha equals 0.05. From the t-distribution table, the critical t-value for 4 degrees of freedom at alpha equals 0.05 for a two-tailed test is 2.776. Next, we use this critical t-value to make a decision based on our calculated t-statistic. Decision rule. If the absolute value of the t-statistic t is greater than the critical t-value, we reject the null hypothesis. If the t-statistic is greater than 2.776, the critical t-value, we reject the null hypothesis. Conclusion. The significant t-value indicates that the difference in test scores before and after the new teaching method is not just due to random chance. Instead, it is likely because of the teaching method itself. This result suggests that the new teaching method had a statistically significant effect on improving the students' scores. Summary. Today, we have covered 1. Pre-experimental data analysis. 2. Calculated essential statistics, mean, variance, and standard deviation. 3. Performed a paired t-test to determine if the observed changes in test scores were statistically significant. Our results show that the new teaching method had a significant positive impact on students' test scores. Call to action. If you found this video helpful, please like, share, and subscribe to the English Simplified channel for more tutorials. Leave your questions or suggestions for future videos in the comments below. Thank you for watching, and I'll see you in the next video.